Okay, so I'm going to make this video to go over topic 3 review questions worksheet. Question 1a says define internal energy. So remember, in any object, whether it's a solid, liquid, or gas, it's made up of millions and billions and trillions of atoms and or molecules. And each of those molecules is in random motion. And therefore has each individual molecule or atom has kinetic energy and possibly potential energy associated with it. The internal energy of a substance is just the total kinetic energy of all those atoms or all of those molecules plus all the potential energy between the atoms and molecules. Okay, so in a way it's kind of like mechanical energy. Mechanical energy is the sum of kinetic and potential energy of an object. Internal energy is the total kinetic energy of all of the trillions and trillions of those atoms, or the trillions and trillions of those molecules, plus all of the potential energy each one has. Question 1b is a problem involving the ideal gas law. 1b says 0.46 mole of an ideal monatomic gas is trapped in the cylinder. The gas has a volume of 21 cubic meters and a pressure of 1.4 Pascal. State how the internal energy of an ideal gas differs from that of a real gas. So the primary difference as far as internal energy goes is, I said before, internal energy is the sum of an object's internal kinetic energy, that is the kinetic energy of all of those atoms or all of those molecules, and all of its potential energy, all of the potential energy between each individual atom or molecule. Now, in an ideal gas, we assume that there's no interaction, that the particles of the gas have no interaction between each other, and therefore, in an ideal gas, there is no internal potential energy. Okay. Now, in a real gas, we can't make that assumption. In a real gas, the particles of the gas do interact with each other, and therefore, the difference as far as internal energy goes between an ideal gas and a real gas, in an ideal gas, the internal energy has to be 100% kinetic energy, because, like I said, in an ideal gas, we're assuming there is no potential energy between the gas particles. In a real gas, there is. Determine in Kelvin the temperature of the gas in the cylinder. This is a problem using the ideal gas law. Okay, now luckily, if you look at the quantities we're given N equals 0.46 moles, and the volume is given in SI units. That's good. We don't have to do any conversions. And the pressure is also given in SI units as 1.4 Pascal. Okay, and so this is going to be a very simple application of the ideal gas law. The ideal gas law is PV equals nRT. Now, it's important that you show your work when you're doing these problems, and part of that is rearranging the equation given for what you're solving for. So in this case, we want to determine in Kelvin the temperature of the gas in the cylinder. Keeping in mind, in any equation with temperature in it, it's implied that the temperature must be in Kelvin, because that is the SI unit for temperature. So T equals PV over nR. Okay, this is a 2-point question right here, and so this is 1 point right here. And from here, it's just a matter of plugging values in for P, V, N, and R in SI units is 8.31. Okay, so I'm going to do that calculation really quickly. The temperature I get is approximately 7.7 Kelvin. Okay, that's for this question here, 1b2. 1b3 says, the kinetic theory of ideal gases is one example of a scientific model. Identify one reason why scientists find such models useful. Okay, so models in science are useful for a variety of different reasons. One reason is because they can be used to make new predictions or new hypotheses about other discoveries in science. They can be used to explain previous observations or previous experiments. And even though in a lot of situations models are not necessarily 100% aligned with reality, they're a really useful starting point to help us kind of understand and conceptualize very complicated concepts. Okay, so again, just to list out a few applications of models in general in science, they can be used to make predictions, explain observations, or just to simplify and help us conceptualize complicated situations. Question 2, a substance is heated at constant power. The graph shows how the temperature T of the substance varies with time t as the state of the substance changes from liquid to gas. What can be determined from the graph? So if you're looking at this graph, this object is being heated at a constant power, and so what that means is as time increases, basically it's the same as saying that we're adding more and more heat to the object. Now, here where you see a temperature increase here, this first temperature increase is going to correspond to an object becoming being heated up while it is still a liquid. Here is going to be the phase change, and the reason I know, and let me just label this, here we have the phase change. I know that during a phase change, right, that the temperature of a substance does not increase, and the reason for that is as you add heat during a phase change, all the heat that you put in is going to breaking the bonds between the molecules that make up the substance. And so, because there's no heat left over to increase the kinetic energy of those atoms or the kinetic energy of those molecules, the temperature doesn't change. So here we have a phase change going from liquid to gas, and after that we have a temperature change as the substance is now completely turned into a gas and is free to increase its temperature. Now, as far as this question goes, we need to kind of understand conceptually what is specific heat capacity telling us. Okay, and the name is kind of a misnomer. Specific heat capacity doesn't have anything to do with capacity or how much heat something can store. Really, the number itself tells us how easily does an object's temperature change. For example, a low specific heat capacity corresponds to an object changing its temperature very easily. For example, metals tend to have very low specific heat capacities because it's easy to heat up a metal, right? That's why we make pots and pans out of metal, so when we put them on the stove, their temperature changes very quickly. Objects that kind of resist changes in temperature, such as water, have a high specific heat capacity. So looking at this graph, we can tell that during the temperature change while the substance is a liquid, we can see there's a temperature change that happens much quicker, and once the substance is turned into a gas, its temperature doesn't change quite as quickly anymore. And so what that means is, while it's in its liquid stage, right, the substance has a much lower specific heat capacity than when it is become a gas and doesn't change its temperature as quickly. So if we look at these answer choices, A says the specific heat capacity of the gas is smaller than the specific heat capacity of the liquid. So okay, so we know that's not true. I just said that the specific heat capacity of the liquid is clearly smaller because the temperature change happens much quicker on the left side of this graph. So A is out, and then B is basically saying the opposite, and so B is going to be the correct answer. Now, C and D are not acceptable as answer choices, and the reason is they refer to the latent heat of fusion and the latent heat of vaporization. Now, latent heat in general has to do with phase change. As we can see from this graph, there's only one phase change. Okay, and so there's no possible way that we can tell any information about being able to compare two latent heats of the substance because we're only given information about one phase change in the graph. And so the correct answer for 2 is going to be B. Question 3, which of the following is not an assumption of the kinetic model of ideal gas. This just goes down to knowing what are the assumptions of the ideal gas model. A, all particles in the gas have the same mass. That is an assumption of the kinetic model. In the kinetic model, we assume that all particles are identical. However, if you look at B, all particles in the gas have the same speed. That is not an assumption of the kinetic model of ideal gases. And in fact, remember, real substances are made up of a bajillion tiny little gas particles, right? There's no possible way that each particle, or that every single particle in the gas can have the same speed, because they're continuously colliding with each other and colliding with colliding with the container walls. And so B, there's no possible way that is true. C and D are, in fact, assumptions of the kinetic model of ideal gases. And so, again, the correct answer is going to be B for question 3. Question 4A. Okay, so question 4A, we have another free response question. It says, in an experiment to determine the specific latent heat of fusion of ice, an ice cube is dropped into water that is contained in a well-insulated calorimeter of negligible specific heat capacity. The following data are available, and they give us all of this information. And if you are, if you're kind of paying close attention, you might recognize that this situation looks familiar, and the reason is because we've actually done this experiment before in IB Physics 1, where we dropped pieces of ice into a well-insulated container, measured the initial and final temperature, and used that to calculate the specific latent heat of fusion of ice. And so the concept behind doing this kind of question is that if we have a well-insulated container of negligible specific heat capacity, what that means is that the heat, let's say the heat going into the ice is equal to the heat lost by the water. Right. Now I put these bars here to kind of mean absolute value, so these are equal in magnitude, not necessarily equal in sign. This is going to be a negative Q, right, because heat is being lost by the water, and this is going to be a positive Q because heat is going into the ice, but in magnitude these are going to be the same. And so let's kind of break down how this is going to work. The heat lost by the water, let's say Q water, is equal to, I'm going to write this down here, the mass of the water times the specific heat capacity of the water times the change in temperature of the water. Now, in the problem, the initial and final temperatures of the water are given, and so we can kind of go ahead and write out the right side of this equation over here. The mass of the water is 300 grams. Watch out for units. That is going to be 0.35 kilograms. Specific heat capacity of water is given at 4,200. And delta T of the water is going to be -6. Okay, -6 Kelvin. Now, I said before that even though this equation, the two sides are equal in magnitude, this heat lost by the water is negative, and so to kind of account for this negative sign, I need to add another negative sign over here. You might remember from last year, we wrote this as Q out equals minus Q in, and that's kind of where this negative sign comes here. Basically just a kind of a bookkeeping thing, so that you understand that even though this is basically conservation of energy, right? Heat going in to something must come out of something else. So to make the math and the signs come out, we have to kind of artificially put in this negative sign here. Now the heat going into the ice, this is a little bit more complicated, because there's two things that happen to the ice. Okay, the first thing that happens to the ice is that it phase changes, right, and it melts. And if we wanted to calculate, how much heat does it take to melt some amount of ice, the equation we would use for a melting phase change would be the mass of the ice times LF, where LF is the latent heat of fusion of ice, and that's actually the unknown in this question. Okay, so once the ice melts, what are you left with? Well, when ice melts, you get water. So what happens to the water? When the ice cube melts, you're basically left with very cold water, right? The ice cube had a temperature of 0 degrees Celsius, the ice cube melts, and so you're left with water at 0 degrees Celsius. Well, that water has to end up at the final temperature of 12 degrees Celsius, and so not only do we have a phase change here, right, we actually have a temperature change also. So the heat that goes into the ice is split, and the way I'm going to write this is I'm going to write the mass of the water, or I should say the mass of the ice cube, is 0.025 kilograms times LF plus the MC delta T, oops, that should be 4,200 there, and the delta T is going to be 12, going from 0 degrees once it's melted to the final temperature of 12 degrees Celsius. Okay, and so basically what we want to do here is do a little bit of algebra, solve for LF. If you do that correctly, if you do the math correctly, your answer for LF should come out to be about somewhere about 3.02 times 10 to the 5 joules per kilogram. Okay, somewhere in that ballpark. Hopefully if you do the algebra correctly. So, take a moment to look at that. Okay, moving on, 4b, the experiment is repeated using the same mass of crushed ice. Suggests the effect, if any, of crushing the ice on 1, the final temperature of the water, and 2, the time it takes the water to reach its final temperature. So, the form of the ice, whether it's crushed or cubed or whatnot, has no effect on the final temperature of the water. The reason for that is, if you think back to the calculation we just did, we're doing it in terms of heat and energy, and the shape of the object doesn't really change any of that, right? It really just depends on mass, no matter how that mass is distributed. What is going to change, though, is it is going to happen faster. The ice is going to melt faster if it's crushed, and the reason for that has to do with the surface area of the ice. If it's spread out over a wider surface area, it takes less time to melt, and so it takes less time for the water to reach its final temperature. Okay, so that's going to be 4b. 5. A container holds 40 grams of argon-40 and 8 grams of helium-4. What is the number of atoms of argon over the number of atoms of helium in the container? So my first thought when I read this is, when I think number of atoms and it's talking about gases and all this stuff, I'm thinking about moles. Okay, I'm thinking about, is this question really asking me about the mole ratio of how many moles do I have of argon to how many moles I have of helium? Because I know that mole is just a counting number that has to do with the number of atoms, right? So how do I connect what's given to me in terms of moles? Well, so not precisely, but approximately the mass number of an isotope is somewhere close to its molar mass. And what I mean by that is argon-40, the molar mass of argon-40 is somewhere close to 40 itself. So when it says 40 grams of argon-40, I know that that is approximately 1 mole of argon-40. Now, obviously not exactly, molar mass, has decimals in it, but somewhere close to 1 mole of argon-40. And likewise, helium-4, the molar mass of helium-4 is approximately 4. Okay, and so you can think we're basically making an approximation in this question. These are not precise ratios, but approximately 8 grams of helium-4, if the molar mass of helium-4 is 4 grams per mole, and we have 8 grams, then that means we have about 2 moles of helium-4. Okay. And so if we have 1 mole of argon and 2 moles of helium-4, basically what we're saying is that we have twice as many atoms of helium as we do argon, and so this ratio of atoms is going to be 1/2. So the correct answer to question 5 is going to be A. Question 6, if we move on, what is the definition of the mole? That just goes back to making sure you understand the definition of the SI base units. The correct answer to that is D. Okay. 7, which of the following is equivalent to a temperature of negative 100 degrees Celsius? That's basically a knowledge question, but it's not even really a knowledge question, because if you look in your data booklet, the conversion factor is given to you now, and so the correct answer to that is C. So question 6 is D, question 7 is C. Question 8, during which stage or stages is or are there an increase in the internal energy of the copper? And so this graph is showing us how the temperature of copper changes as it's heated over time. Now, this is kind of a tricky question, and you really need to go back to number 1, where we talked about what is the definition of internal energy. And internal energy, again, is the sum of an object's kinetic energy and potential energy internally. And to be more specific, I mean, if you take this piece of copper and you look at all of its atoms, I don't know how many you have, but all bajillion of these copper atoms, and if you take the kinetic energy of every single atom and you add up all of those kinetic energies, and you take the potential energy of each copper atom and you add up all of those potential energies, and you add those two quantities together, that is basically the internal energy of the piece of copper. And so anything that changes the potential energy of the atoms of the copper, or the kinetic energy of the atoms of the copper, is going to result in an increase in internal energy of the copper. So during P, we can see there's a temperature change, right? And so if there's a temperature change, that means there's a change in kinetic energy of those atoms. And so during P, there's definitely an increase in internal energy. And the same thing goes for R. So P and R are definitely areas where the internal energy is increasing. Now, what about Q? If you look at Q, there's no temperature change. And if you're not careful, you might think, well, if the temperature is not changing, the internal energy is not changing. But that can't be, because during this whole time process, we're melting a piece of copper. We're continuously heating it all the time. During Q, the reason there's no temperature change is because all that heat we're pumping in isn't going to the kinetic energy of the atoms, it's going to the potential energy of the atoms and the phase change itself. So even though you can't see a temperature change, there's still an increase in internal energy of the copper during Q. So in fact, P, Q, and R, at all of these time intervals, there is an increase in internal energy, so the answer is A. Okay, question 9. It says, Matilda raises the temperature of water in an electric kettle to boiling point. Once the water is boiling steadily, she measures the change in the mass of the kettle and its contents over a period of time. The following data are available. Okay, and we want to determine the specific latent heat of vaporization. The specific latent heat of vaporization of water. And again, this is basically going to be kind of a conservation of energy question. Okay, so let's kind of think this through. Once the water is boiling, right, it's continuously phase changing from liquid to gas. In an electric kettle, what that means is that over time, you lose mass because the water is turned into steam, and the steam flies out the end of the kettle. And so that's the reason here you see the final mass of the kettle and water is less after 300 seconds because, well, that steam is gone, right? Now, when I see time and power side by side, my first thought is, what is the main equation for power? That is basically the rate at which energy is used or dissipated, in this case, dissipated. So what is this actually saying? Power dissipation in the kettle. That's saying that, that the kettle loses energy, or I guess you could say energy goes into the kettle at a rate of 2,500 joules per second, right? 2.5 kilowatts. That's 2.5 thousand watts. That's every second 2,500 joules. Okay, so where does that energy go? It goes into the phase change. Okay, so how much energy ends up going into the kettle? That's just 2,500 times 300. So the Q into the kettle is 300 times 2,500, just using this equation to solve for energy. And that comes out to be 300 times 2,500 is 750,000 joules. So we put in 750,000 joules, and what do we get for that? Well, we have water that is already at the phase change point, so 100% of this energy is going to go into phase changing. Alright, so how much phase change can we get out of that? How much mass can we phase change over that 300 seconds? So let's see, if we know that Q equals mLV, and we know that we put in 750,000 joules in order to phase change some mass, right? We know what the mass is. That is just 1880 minus 1580. That's 300 kilograms. Then we can solve for LV pretty easily using basic math. LV is equal to approximately... Okay, sorry, quick correction. Now that I look at this more carefully, I see this is not 1880 kilograms. This is 1.880 kilograms, and this is 1.580 kilograms. And so instead of having the mass be 300, this should actually be about 3. And so LV, if you divide this out, is about 250,000 joules per kilogram. And that is my latent heat of vaporization for water. Question 2, outline why your answer to B1 is an overestimation of the specific latent heat of vaporization. Questions like this usually are kind of comparing what did we do in the calculation and why is it not necessarily realistic. The reason it's not realistic is because we're assuming that there's 100% energy transference, and there's not. In reality, energy could be transferred to the surroundings, and so what that means is the value we calculated is actually bigger than it's supposed to be, and so our final answer is really an overestimate. Right? In reality, this 750,000 joules is going to be less than that because we lose some of this heat from the kettle, and so the true value of LV should actually be a little bit lower than what we found. Okay, moving on. Question 10. The specific latent heat is the energy required to change the phase of 1 kilogram of a substance at constant temperature. So that should be D for question 10. D. Question 11. An ideal gas is contained in a thermally insulated cylinder by a freely moving piston. The gas is compressed by the piston, and as a result, the temperature of the gas increases. What is the explanation for the temperature rise? Okay, so you need to be careful in this question. Temperature is directly tied to the average, or sorry, I should say, the average kinetic energy of the gas particles. Now, A is true. The problem is that A has to do with pressure. B is the correct answer, and again the key word here is energy is transferred to the molecules by the moving piston. So the moving piston moves, runs into those gas particles, gives them more energy, and therefore they have a higher temperature. Okay, C is true, D is true. The problem is only one of these explains temperature, right? So understand, what is temperature? A measure of the average kinetic energy of those particles. Question 12, a mass of 0.2 0.2 kilograms of water at 20 degrees Celsius is mixed with 0.4 kilograms of water at 80 degrees Celsius. No thermal energy is transferred to the surroundings. What is the final temperature of the mixture? So this is a very basic calculation, a very basic let me just erase that. Very basic calculation using the concept we talked about earlier. I don't like that. The Q out equals minus Q in concept, but this is a very simplistic problem because the two objects we're talking about are both water. And so even if we were to write this out, let's say the 0.4 kilograms of water represents Q out. We have MC delta T is TF minus 80, and Qn is going to be 0.2 times 4200 times TF minus 20. I'm going to rewrite this over here, 0.4, and if you notice there's a 4200 on both sides, I'm just going to leave that out of the final equation over here. 0.4 times TF minus 80 equals minus 0.2 times TF minus 20, and if you solve this out using basic algebra, actually I'll go ahead and do this now. Remember, this is a multiple choice question, and on the actual IB exam you can't use multiple choice questions, or sorry, you can't use a calculator with multiple choice questions. So I would just kind of write 0.4 TF minus 0.4 times 80 is going to be 32 equals minus 0.2, because there's this minus sign up here, TF plus 0.2 times 20 is going to be 4. Alright, so I get 0.6 TF equals 36. And so TF, if you think of 0.6 as 6 over 10, then we get essentially 36 or 360 over 6, which is 60 degrees Celsius. So the answer is D. Question 13 is just a definition question. The answer is A. Obviously, I'm going to pause it there if you're still looking at question 12. Okay. Question 14 is just understanding that temperature is directly proportional to the average random kinetic energy of the molecules of a gas. The answer is C. And question 15, again, definition question, going back to our question number 1, actually, what is internal energy? Here it is. Okay, this is the definition of internal energy. The correct answer for 15 is B. So, I hope that helped. Let me know if you have any other questions.